Hello, beautiful souls, and welcome to my channel. Welcome aboard, as we set sail on a journey through Gamow factor. The Gamow factor, Sommerfeld factor or Gamow-Sommerfeld factor, named after its discoverer George Gamow or after Arnold Sommerfeld, is a probability factor for two nuclear particles' chance of overcoming the Coulomb barrier in order to undergo nuclear reactions, for example in nuclear fusion. By classical physics, there is almost no possibility for protons to fuse by crossing each other's Coulomb barrier at temperatures commonly observed to cause fusion, such as those found in the Sunday When George Gamow instead applied quantum mechanics to the problem. He found that there was a significant chance for the fusion due to tunneling. The probability of two nuclear particles overcoming their electrostatic barriers is given by the following equation. P at x equal E cert I at x di, where Eg is the Gamow energy. Eg Rix Osb. Here, m at x to alfrac mit x to m at x mit x to plus m at x is the reduced mass of the two particles. The constant is the fine structure constant, c is the speed of light, and z and zb are the respective atomic numbers of each particle. While the probability of overcoming the Coulomb barrier increases rapidly with increasing particle energy for a given temperature, the probability of a particle having such an energy falls off very fast, as described by the Maxwell-Boltzmann distribution. Gamow found that, taken together, these effects mean that for any given temperature, the particles that fuse are mostly in a temperature-dependent narrow range of energies known as the Gamow window. In this chapter, we'll be shedding light on derivation and its role in shaping our understanding. Gamow first solved the one-dimensional case of quantum tunneling using the WKB approximation. Considering a wave function of a particle of mass m, we take area 1 to be where a wave is emitted, area 2 the potential barrier which has height v and width l at 0xl, and area 3 its other side, where the wave is arriving, partly transmitted and partly reflected. For a wave number k and energy east we get ex I eat bx bx kx kx I eat, where k cert me and k cert movi. This is solved for given a and by taking the boundary conditions at the both barrier edges, at x0 and xl, where both and its derivative must be equal on both sides. For Coulomb, this is easily solved by ignoring the time exponential and considering the real part alone. The imaginary part has the same behavior. We get up to factors depending on the phases which are typically of order 1, and up to factors of the order of cert IV assumed not very large, since b is greater than east not marginally. But C1, C approx frackier.fraccheck.erkel. Next, Gamow modeled the alpha decay as a symmetric one-dimensional problem, with a standing wave between two symmetric potential barriers at xl and lx, and emitting waves at both outer sides of the barriers. Solving this can in principle be done by taking the solution of the first problem, translating it by and gluing it to an identical solution reflected around x0. Due to the symmetry of the problem, the emitting waves on both sides must have equal amplitudes, but their phases may be different. This gives a single extra parameter. However, gluing the two solutions at x0 requires two boundary conditions for both the wave function and its derivative, so in general there is no solution. In particular, Ray writing after translation by as a sum of a cosine and a sine of x, each having a different factor that depends on k, and the factor of the sine must vanish so that the solution can be glued symmetrically to its reflection. Since the factor is in general complex, hence its vanishing imposes two constraints, representing the two boundary conditions. This can in general be solved by adding an imaginary part of k, which gives the extra parameter needed. Thus east will have an imaginary part as well. The physical meaning of this is that the standing wave in the middle decays. The emitted waves newly emitted have therefore smaller amplitudes, so that their amplitude decays in time but grows with distance. The decay constant, denoted, is assumed small compared to E. Can be estimated without solving explicitly, by noting its effect on the probability current conservation law. Since the probability flows from the middle to the sides, we have a frac partial tint q club side x equal a dot frac bar me left up c a frac partial up c 1 partial x say a frac partial up c partial x right. Note the factor of 2 is due to having 2 emitted waves. Taking it, this gives a lambda dot frac dot fracture dot equal approx a frac bar me k. Since the quadratic dependence in is negligible relative to its exponential dependence, we may write a lambda prox frac become q frac dot equal. Remembering the imaginary part added to k is much smaller than the real part, we may now neglect it and get a lambda prox frac become dot r frac of x dot e to mov bar. Note that our frac is the particle velocity, so the first factor is the classical rate by which the particle trapped between the barriers hits them. Finally, moving to the three-dimensional problem, the spherically symmetric Schrödinger equation reads expanding the wave function ρ in spherical harmonics and looking at the nth term. Our frac bara left frac chidra freka frac chidra left of our frac bara frac nina aiche. Since n0 amounts to enlarging the potential, and therefore substantially reducing the decay rate given its exponential dependence on cert of E, we focus on n0, and get a very similar problem to the previous one with r, except that now the potential as a function of r is not a step function. The main effect of this on the amplitude is that we must replace the argument in the exponent, taking an integral of r to mod e bar over the distance with e rather than multiplying by L. We take the Coulomb potential of r frac as z p ver epsilon 0r. Where is the vacuum electric permittivity? Either electron charge z equal to is the charge number of the alpha particle and z the charge number of the nucleus z after emitting the particle. The integration limits are then r to r frac as z p ver epsilon 0 e, where we assume the nuclear potential energy is still relatively small, and which is where the nuclear negative potential energy is large enough so that the overall potential is smaller than east. Thus, the argument of the exponent in is a frac cert movement r cert frac rai drive equal r frac cert movement r cert frac urger. This can be solved by substituting t cert and then t cos and solving for giving a got r frac cert movement got cos certax zert x equal r frac certimus z p ver epsilon certs got cos certax zert x, where x r. Since x is small, the x-dependent factor is of order 1. Gamow assumed x1, thus replacing the x-dependent factor by giving a lambda sim e cert I gai with e.g. alpha pim after p ver epsilon bar, which is the same as the formula given in the beginning of the article with z of z, zbzz and the fine structure constant alpha alpha p ver epsilon c. For a radium alpha decay, z equal 88, z equal 2 and meters equal p, e.g. is approximately 50 give. Gamow calculated the slope of log with respect to east at an energy of 5 MeV to each, compared to the experimental value of. If you found this video helpful, give it a like and share it with someone who might benefit from it.